So the presentation is the Elusive Universe, and it's part B, part A having been presented back in October. So part A posed the first two of four questions. First question was, how long has humankind been trying to understand the universe? The second question is the universe our friend or our enemy, and why? And these two questions, the answers to them set up tonight's presentation. So I'm very briefly just going to reprise the high points from part A. So the Greeks proposed the atom in 400 BCE. This was really starting in 600 BCE. The Greeks began the process for humanity to contemplate what was the universe and what is it composed of. So Democritus brilliantly proposed the existence of an indivisible, tiny constituent of everything that he named the atom, which means indivisible in Greek. But it was not until the 19th and early 20th centuries that seven scientists discovered it and its inner structure. And I should point out that one of the biggest critics for Democritus was Socrates, who felt that if you couldn't see something, you couldn't rely on it as an explanation for a phenomena. So although Democritus actually directionally got it right a long time ago, it really wasn't until the 19th and early 20th century that Dalton proposed atomic theory. He's on the upper left. The Curies discovered radioactive delay. Thomson discovered the electron, which was a real jolt because the discovery of the electron indicated that there actually was something that was even smaller than the atom itself. Rutherford discovered the nucleus, Einstein Brownian motion, and Chadwick on the lower right discovered the neutron. And by that point, we had a pretty good idea of what made up the atom. Since then, we've identified the basic particles that comprise the entire universe. This is known as the Standard Model. We now know and have known since the late 1950s that protons and neutrons are not basic like electrons are. As a matter of fact, protons and neutrons are made up of point-like particles that have become known as quarks. The most important ones on the upper left are known as the up and down quark. And a proton has two up and one down, a neutron has two down and one up. There's also electrons and neutrons in the basic universe, and four basic types of force-bearing particles, not counting the potential graviton or the Higgs, which we'll get to. So it could be just these eight, but it's not that simple. As a matter of fact, it's 17 plus the likely graviton. And in case you're interested in how they're grouped, bosons are force-bearing particles, fermions are the class of particles that have mass, leptons are electrons and neutrons. You've probably heard these terms before. Hadrons are particles that are made of quarks. And of these, baryons have three quarks, namely protons and neutrons, and mesons have two, which are very short-lived particles that usually are created in cosmic ray collisions. Bose, by the way, was a very important Indian theoretical physicist in the 1920s who had a lot of breakthroughs in the field of quantum mechanics. So Homo sapiens have walked this planet for about 270,000 years, and our application of science spans just the most recent 1% of this period. And it's fair to say we just haven't had enough time to know all we seek about the universe. And of course, we all understand that the elusive universe did not come with an operating manual, and it sort of dares us to deduce how it works. And We are handicapped because we are confined to the surface of the Earth and the lower portion of our atmosphere, uh, unless we have life support. So it's not as if we can zip through the universe at will and observe things close at hand in order to be able to verify. We have to do everything from the Earth's surface and with the aid of robotic spacecraft, and that's a challenge. Now, the first second of the universe was the most important second in all of time. As you may remember, it's divided into six epochs that lead from the quantum soup to the formation of protons and neutrons. After that, it takes 380,000 years before the universe cools sufficiently for photons to be released and for the first light to actually be uh, speed throughout the cosmos. And the first light, as we know it, is called the cosmic microwave background. And you can see that on the lower right. We'll talk a bit more about that in a second. Uh, Now, in part B of this presentation, we're going to pose the final two questions. Question three is, what variables are fine-tuned for life? And question four is, how did the universe begin? In other words, what came before the Big Bang? So in terms of question three, what variables are fine-tuned? Scientists have identified approximately 100 such factors, but we're going to talk about the nine most significant. And the first is the relative strength of the four fundamental forces. The ratios happen to be critical. Each has to be set within a narrow range, and they are vastly different in terms of strength. So let's take a look at them. Um, if we were to assign a relative strength ratio to the four fundamental forces on a scale of 100, the strongest would be the strong nuclear force, and it would get a rating of 100. The next strongest is the electromagnetic force, which would get a rating of 1. Then the weak nuclear force, which is 10 to the minus 11th. And finally, gravity is almost infinitesimally weak. Uh, to talk briefly about the four forces, the strong nuclear force has one vital uh, use or purpose, and that is it binds quarks together inside of protons and neutrons. It is so strong that you cannot break quarks apart. Uh, you can use the analogy that it's something like a rubber band in that the more you stretch it, the stronger it gets. Uh, the electromagnetic force is very important in the operation of the sun or stars, and it also governs interactions between electrically charged particles um, that hold atoms together. And it's responsible for responsible for the electromagnetic spectrum, which, as we know, includes that portion of visible light, which is so critical to our ability to understand and see what's happening. But visible light is only a small portion of the electromagnetic spectrum, which runs from high energy gamma rays to low energy radio waves. The weak nuclear force, which I was unfortunately starting to jump ahead to, is about a millionth to 100 trillionth the strength of the nuclear strong force, and it's responsible for certain types of radioactive decay. The gravitational force, by far the weakest, is responsible for, why we don't fly off the surface of the Earth, for example. And, many people look at this number and they say, well, it can't be right because gravity is a very strong force. But in reality, it takes the entire mass of the Earth to hold you to the surface. And if you fall from a high altitude or from a high, high altitude, it's not gravity that's causing you the pain when you hit the ground, believe it or not. It's the electromagnetic force that's holding the atoms and molecules together of whatever substance you hit. So another thing that's fortunate about the basic variables in the universe is that neutrons are slightly heavier than protons. This mass difference stabilizes the nucleus. The preference for neutrons to decay into protons is very important because if protons were heavier, they would prevent stable hydrogen from forming, and this would wreck stars that rely on hydrogen and prevent the creation of heavier elements, ultimately making life as we know it impossible. One point that I wanted to make before we go on is when I talk about life in the balance of the presentation, I'm talking about carbon-based life, which means you and I. There may be other types of life that are based on, say, silicon or perhaps methane, but tonight, if I say life, I'm really referring to our type of life. I didn't mean to do that. So the mass energy distribution, the speed of light, and the electron to proton mass all must be what they are. And what's very fascinating is that the electron is 1,836 times smaller than a proton. And yet they each have equal and opposite charges. And when you think about that, this tiny electron possesses as much, oomph um, negatively as a proton has positively. There's also the fine structure concept, which is the strength of electromagnetic interaction. If it were serious, if it was significantly different, we'd have no stars or only short-lived stars, and the universe would not be able to evolve. The value of this ratio, by the way, has to be highly specific. Many scientists have characterized it as being as pinpoint as a pencil balancing on its tip. Now, the age of the universe, we need to have a relative expansion of the universe to enable enough time for life to appear. Multi-generations of stars have to form and die in order for heavy elements to seed life-supporting solar systems like our own. And for that reason, 13.8 billion years is what it takes. The expansion rate, I hinted on this earlier, if the expansion rate of the universe had been, or it was, or is greater than it currently is measured to be, um, the universe could not exist as we know it. The expansion rate is basically due to dark energy, which is a type of repulsive gravity. At least this is our basic understanding. And even though its value is extremely tiny, the sheer amount of it is what causes it to overcome, if you will, the attraction of gravity. And the other thing that's rather insidious is that as space-time expands and more space is created, more dark energy comes into existence, which therefore increases the rate of expansion. Now, to me, this is the most fascinating of all of the variables. It's called the triple alpha process, and it is the name for the process that is essential in order for carbon to be forged inside of the cores of dying red giants once their temperature reaches 200 million degrees Kelvin. Now, by contrast, our sun's core is 18 million degrees Kelvin. Our sun fuses, like all mainline stars, uh, main sequence stars, is only capable of fusing helium. So if you want to go to carbon, you literally have to get carbon from uh, shrinking cores from red giant stars. So even though the red giants are bloating out their outer layers, their cores are contracting, the temperature is soaring, and you now have conditions to create the next series of elements. And let's start by saying in order to get helium, which is one of the three of helium, I should say, is um, the basic constitute of what we call an alpha particle. If you strip off the electrons from a helium atom, what's left is the nucleus. The nucleus is known as an alpha particle. You need three alpha particles to fuse to form carbon. So how does the process start? Well, first, you need four hydrogen atoms, and the four protons have to convert to two neutrons and two protons, and then they have to come together and form helium, which is pretty straightforward, and it's what happens all the time inside of main sequence stars. But once a star starts to, once a star has run out of helium, it now starts to fuse helium into heavier elements, beginning with beryllium. So a beryllium nucleus is simply two alpha particles fused together. And that seems simple enough. If you have enough heat, you would think that you can just, inside the red giant, you can fuse these two helium alpha particles and get beryllium. The problem is the energy required to fuse beryllium is just about the same as the energy required to break down beryllium, which means that an incredibly small portion of beryllium survives for any period of time. As a matter of fact, the half-life of beryllium is 10 to the minus 16th seconds. That means if you were a beryllium nuclei or nucleus, a lightning flash would be an eternity to you. But because the core of these red giants is so compacted, at any given moment, some beryllium nuclei uh, exist. And there's enough time for a third alpha particle to fuse to form carbon 12. But there's another problem. As nice as this appears, carbon 12 is equally unstable and immediately wants to break back down into either beryllium or into three alpha particles, unless it has enough time to emit a photon, which is in the form of a gamma ray. So if not for the compactness of the core and the vast amount of fusing that's taking place, there simply would not be enough opportunity for beryllium to form carbon and for some carbon nuclei to hang on long enough to emit a photon and stabilize. So this is what the process looks like. And one more thing to mention is that if a carbon nucleus is fused with another alpha particle, we get oxygen. We get, O16. So the two most important elements for life depend on this extremely delicate process. Now, the triple alpha process was really deduced by Fred Hoyle. And I'm not sure how many of you remember Hoyle from the 50s and 60s, but he was kind of like the Stephen Hawkings of his day. He was the most famous astronomer, and he's known for one of his biggest goofs, which is his determination to push the so-called steady state theory of the universe and not to adopt what we now know as the Big Bang and the eternal expansion of the universe. As a matter of fact, Hoyle was so, if you will, disrespectful to the idea of a expanding universe that he called this uh, theory the Big Bang. So we owe it to Hoyle in his moment of derision for the name that we have so readily adopted for how the universe began. But on the positive side, the problem that was besetting physicists in particular in the 50s and 60s is that it looked like it would take 1 billion degrees inside of the core of a red giant to fuse carbon, which obviously was wrong because no star is that hot. It was Hoyle who figured out that one of the quantum levels necessary or that would be feasible, I should say, to create alpha particles was simply missing. Somehow the atomic physicists had simply missed it in their testing. Well, Hoyle brought it to their attention. They agreed to conduct particle accelerator experiments, and they found it. They found a level that only required 200 million degrees, which of course is what you find in red giants. And by the way, Hoyle's prediction was 7.7, and as you can see here on the graph, it's actually 7.654. So it was an amazing conclusion on his behalf. So anyway, one reason why I dwelt a little bit on Hoyle is because he was an atheist, but he was so struck by the precision and the balance and the rarity of the triple alpha process that he did not think it could be by chance. He calculated the margin for error in this process was only 0.5%. And I'm going to tell you why that's so critical or why it's so narrow in a moment. But he thought that there had to be intelligence behind the creation of all of the uh, variables that make the universe so right for life. Um, you might think that if the process was more forgiving and we actually had more carbon created inside of stars before they blow up and form supernova or planetary nebula, you might think that that would be an advantage, that we actually would have more life. But as it turns out, if we had more carbon in the universe, we'd end up with more planets that had carbon cores. In other words, diamond cores, which I know sounds wonderful, but it's not. And the cores would cool faster. They would not permit tectonic plate activity, which reconstitutes the surface of the planets. They would not, most importantly, engender an elect or a magnetic field to protect the planet. And all we have to do is to look at what happened to Mars to see what happens if you don't have a magnetic field. So that's what would happen if too much carbon was produced. And of course, if it was the other way around and we had too little carbon, then life would be very rare. So the ingredients in the recipe of the Big Bang were remarkably balanced and complete. Everything that we needed to create the universe, it was there and in the right proportion, which may seem intuitive, but it's really remarkable, I think, when you think about it. So the question then becomes, how did the Big Bang know to produce just the right proportion of completely uniform quarks, leptons, and force bosons rather than, say, inert sterile bits? And then why is it governed by consistent mathematical laws that are and is so perfectly flat? Well, we're going to answer those questions. Uh, Before I go on, I just wanted to point out that you have to ponder if you don't quite grasp the significance of this, but it's worth pondering that all of the electrons, for example, are the same throughout the universe. The ones that are in your body are the same as the electrons that we find in the Andromeda galaxy. And we're used to variations. We're used to things not being uniform. We're used to mutations. But everything in the universe is completely uniform by type. And then finally, let's not forget that local conditions must be just right in order for life to exist. You need liquid water on the surface of a planet. You need a large moon with a specific rotational period to stabilize a planet's axial tilt. The Earth's mass enables it to retain an atmosphere and have geological activity. And the orbit of the Earth lies near the inner edge of the habitable zone and has a low eccentricity. So all of these have to be uh, within the variables that control the possibility for life, like a planet similar to Earth. And in particular, our solar system happens to be located in a region of the galaxy that is relatively free from harmful galactic events. So they all have to be present. And on a lighter note, there's one of six quarks. The other four heavier quarks are very short-lived. One of them is called the strange quark. It helps determine if a supernova contracts into a black hole or into a neutron star. And this matters because if this quark was just a little heavier, there would be fewer neutron stars and therefore less jewelry on Earth. And that's because precious metals are only created in neutron star collisions. So just a reminder, we have the standard model with 17 fundamental particles and their anti-equivalence plus gravity, and the Higgs boson, which is the boson that provides mass. And we're going to see that with just a bit more detail shortly. We also have what we consider to be a theory of everything based on the standard model. So we have made progress as long as we are on the right track. So having contemplated the balance and uniformity throughout the universe, we've set the stage for the final and most provocative question of all, which is, how did the universe originate? And until the past few years, debate was very energetic about this. But most scientists are now certain that the Big Bang was not the beginning. Recent findings solve all the nagging problems with the classic bang. And this is significant. One of the reasons why the Big Bang, I think, was always held in skepticism as the ultimate beginning is because it couldn't answer four basic problems. But the solution turns out to be quantum field theory and inflation. But don't be frightened by the implication that we're going to get into heavy science here and maybe a lot of math. It's actually fairly basic. So, according to Sean Carroll, quantum physicist and cosmologist at Johns Hopkins, quantum field theory is the single best way we have of describing the universe at its deepest level. We no longer need to consider fields and particles separately thanks to quantum field theory. All particles pop out from their fields, which, by the way, explain their uniformity throughout the universe. Inflation came before the Big Bang. This is almost a certainty. Prior to inflation, the universe that we see today was microscopic. There was only one field, and it was called the inflaton or the inflation field. You can take your pick as to which one you prefer. And at the quantum level, everything is roiling. A quantum fluctuation set off inflation. Let me just take a moment and say that quantum theory has been proven many, many times. And basically, on the quantum level, which is the subatomic world, there is no continuity. There are jumps. There are jumps in energy level. There are jumps in distance traveled and speed and whatnot. And so, because it's not continuous, it's roiling. And so, a fluctuation is believed to have set off the inflation of space-time, or empty space, I should say. That's not space-time yet, just empty space. Time did not yet exist. The expansion was breathtakingly fast once it started. It basically became runaway. The father of inflation, Alan Guth, calculated that space expanded by a factor of a trillion times in one of our tiny fractions of a second. And as noted, empty space is a sea of quantum activity. So this inflation or inflaton field was filled with uh, energy in every square meter. And so the newly inflated pre-universe had a lot of energy to work with. Now, normally speaking, particles in what we consider to be the vacuum come in and out of existence very quickly, and they are balanced. You have a positive proton and you have an antiproton, and they turn into energy and disappear. But when this process supercooled and stopped, the total amount of energy was released, and it was enough to create the universe that we know today. Uh, at that moment, all the energy converted into mass and light, and this was the real Big Bang. So, German polymath Leibniz famously asked, why is there something rather than nothing? Well, Lawrence Krauss, who is a somewhat controversial astrophysicist, believed that a key concept is that empty space isn't truly empty. It's boiling, it's bubbling, like we just talked about. Its total energy actually nets to zero, so a universe can emerge from nothingness without violating conservation laws. The first thing created after the Big Bang was not particles, it was quantum fields. As you'll see, particles are simply excitations in these fields. Fields beget particles. And there is a field for each of the 18 types of particles. There's an electron field, an up quark field, a photon field, etc. Now, we actually know invisible fields from everyday experience. We've all are aware of these three fields that I'm going to show you here. The thermal field in a room, the gravitational field throughout the universe, because we can feel that, and the magnetic field. Now, a thermal field is due to a heat source in a room. If you were to map every point three-dimensionally in a room, you would get a reading on temperature. And that would be the thermal field in that room. And by the way, the temperature would be quite a bit different, as you went from right in front of the heat source to the far corners. The gravitational field is the bending of space-time according to Einstein. And we all know magnetic fields from when we were kids and we played with magnets and tried to force the north poles together of two magnets. So following the Big Bang, 18 quantum fields appeared. Particles are actually energy bumps in a quantum field. So let's say this was the electron field. When enough energy exists at a particular point in this electron field, an electron appears. And by the way, it's precise. And this is why electrons and every other particle are the same throughout the universe, because you can only have a particular amount of energy to make an electron. Nothing happens until you get double that amount, and then you get two electrons. So a particle is nothing more than a specific excitation in its related field. And after 380,000 years, the universe finally cooled sufficiently for atoms to bind. So we know about the quantum fields, we know all of these particles existed, but the universe was far too hot in order for them to start to come together to form protons, pardon me, for neutrons and protons to actually bond with electrons to form atoms. And this is the image of actually, it's the earliest image we have of the universe, the cosmic microwave background. And I'm just going to show you something else here before I comment on it. We have been imaging the CMB since 1992. And if you look at the three satellites that we've launched since, you can see the amazing increase in detail that each satellite has delivered to us. Now, the cosmic microwave background was discovered by accident in the 1950s, and it literally is the residual of the Big Bang. It's the earliest moment when photons of light were able to escape, and therefore it forms the boundary of the visible universe that we know today, which, by the way, does not preclude the fact that there's a good deal of the universe that's too far away for us to see. I think we spoke about that in the first part of the presentation. So what were the four problems that plagued the Big Bang Theory, the original Big Bang Theory? Well, it was the horizon problem, the flatness problem, the monopole problem, and the breakdown of physics at a singularity. Now, it's somewhat beyond this presentation for me to go into all of the reasons and the explanations, but very briefly, the horizon problem is, why is the universe the same in all directions? The flatness problem is how come parallel lines remain parallel forever? If we had a curved universe, they would merge, they would meet. If we had an open universe, they would bend apart. But for the longest time, it seemed that flatness itself, meaning two parallel lines staying parallel, was virtually impossible to happen randomly. But it's not impossible when inflation precedes what we know as the Big Bang. The monopole problem was simply that there should have been a lot of particles created that literally had just one magnetic pole. And we've never discovered a monopole. And so the question really is, how come? There should be. Well, the answer again, if inflation came first, the monopole problem doesn't exist. And then finally, you avoid completely the breakdown of physics at a singularity because there was no singularity. And by the way, I should also mention that they also believe that on the inside of black holes, there are ways that you can avoid having a singularity so that the problem maybe just goes away completely in every aspect of the universe. So it's comforting though how the universe likely arose apparently from nothingness. But our knowledge of inflation and the Big Bang does not answer these imponderables. First of all, how did the universe know to create 18 perfectly balanced fields after the bang? And what exactly is the essence of each type of particle? Just what is it that gives these, in some cases, point-sized particles a charge or a spin or symmetry or a force? And why does a tiny electron have an equal opposing charge to a much larger proton? Uh, why is it that they actually all do something, that they actually have a characteristic and are not inert? So that leads to the final, summing up is why are there constants and ratios in nature, and why are they set so ideally suited for life? So there's three possible explanations, and I'm going to leave them with you to ponder. There's the Darwinian universe, the random universe, or intelligently designed universe. And the Darwinian universe is a rather new and fairly provocative idea. It suggests that universes have come and gone for a long, long time, and initially they didn't have much form or substance, but each time a new one was created, whatever worked in the prior one remained until finally we were banged into existence in one that had the 18 fields that we just spoke about. The other possibility is one where you just shrug your shoulders and you say there are so many universes that one just had to get it right. And of course, we would only be in a universe that got it right. And the third possibility is that the universe is so amazingly composed and mathematically explainable that it had to be created by a superior intelligence. And uh, it may well be that that intelligence is a product of something that we yet cannot understand. So those are the three choices when we distill them down. Now, for the record, there are other theories that are postulated to explain the universe. Among them, notably, are string theory, quantum loop gravity, and the holographic universe, which hypothesizes that we actually are in a two-dimensional universe that's projected three-dimensionally from its perimeter. Uh, String theory is an extremely fascinating and intriguing idea, but it's only mathematically derived. It can't be proven, and it has so many variables and imponderables that many scientists uh, tend not to embrace string theory, although it does have promise. Anyways, the most important thing for me to say at this point is that all these highly theoretical concepts of the universe might make a great topic for a follow-up presentation, but they are beyond our scope tonight. And with that, I say thank you very much. Somehow the thank you disappeared. There we go. Thank you.
Thank you, Phil.
All right.
You ready for some questions?
Okay, not too bad. 41 minutes, I think. I think we made up some time. I tried to go a little faster.
All
Yes,
right.
ready for questions.
Okay.
Should I stop sharing, Michael?
Share.
I'm going to stop the share. Okay.
Go.
Thank you.
All right. Do we have a question online?
I have a couple questions.
Me
Can you hear
too.
me?
I can hear you, Alan.
All right. Phil, brilliant. Absolutely brilliant. I love just sitting here and watching my brain try to follow those little excitations in the field. But great to think about. I'm
Thank
so
you.
happy we record these. Just a random question. How do we know our sun originated in M67? That was a little bit on one of the.
Oh, you mean from part A? Or was that in there tonight?
It was in there tonight. I saw it.
Yeah, I think the answer is because they know the motion and direction of the sun and they've traced it back to
Okay.
M67. So it's not a big deal. That seems to be, where we came from.
Good. I hadn't heard that before. And my second question is a little more theoretical, and you may have answered it last time or in your summary tonight, but I might have been just daydreaming. Is your conclusion that the universe is friend or foe?
It's a frenemy. It's both.
Okay.
And the reason I say that is because it obviously is a friend because all the conditions exist for our type of life to flourish, but it's an enemy because it confines us. We as a life form just cannot exist in 99.9999% of the universe without life support.
Mm.
And so that precludes strongly the possibility that humankind will ever travel through space unless some technique is derived to travel the equivalent of faster than the speed of light. And by the way, that might be possible if we can fold space-time. That's another whole topic. But basically, we're just confined to the surface, and whatever distance our space probes can travel while being restricted by the speed limit of the universe, which is the speed of light.
Great. I'd love to have an extended discussion on those last three questions, but I yield my time to the Senator Amato, whose hand I saw up.
All right. Mario had his hand up.
I just wanted to comment on Alan's question. It's more than just the orbit. It's the chemical composition of the stars.
Oh, that's right. Thank you, Mario. Thank you.
Yeah.
Yeah. That's right. The similarity between the sun and the stars in M67 is detective's
very
dream.
similar.
Yeah.
My turn.
Arthur.
Thank you. Hey, Phil, thank you so much. It was well worth the wait.
Yeah. Thank you, Arthur.
A few things. I remember reading somewhere that somebody calculated that the entire universe was created from 22 pounds of kilograms of pure energy. That's all it took to actually create the entire universe that we see. The other couple of things I think about is I don't think the graviton exists because you need mass. And the more mass you get, eventually you distort the space it's sitting in. And that's what we call gravity.
I agree with you.
There's no little itty bitty thing you're going to find below an atom.
And by the way, one thing that I can point out is that we know a lot of the facts that I presented tonight thanks to high energy collision of protons and other particles, namely electrons, in particle accelerators. Well, particle accelerators have an upper energy limit. And although we have very impressive um, machines like the LHC, the Large Hadron Collider, we would need a machine that's something like, and I may be underestimating, that would be 10 times the power of the LHC in order to detect a graviton. And of course, the problem with building a machine that massive is who's going to pay for it?
The Chinese seem to want to play with that, but I'll let them do that.
Yeah.
The other thing I was going to mention, a fellow named David Tong gave a lecture at the Royal Institute explaining fields and how everything is made of fields.
Yeah, I've seen that lecture. Yeah,
It's a wonderful lecture.
it really is. He's very, very engaging.
He's done other lectures too. I love
Yeah.
watching the Royal Institute stuff.
Yeah, yeah. Well, it's such a historic location.
Oh yeah,
So
he's
many
doing it for,
great English scientists and
Yeah.
theoretical physicists have spoken there over the years.
yeah. Again, thank you so very much.
Yeah, thank you, Arthur. Yeah, but I think you had some other question that or related portion of what you had asked. Can you remember what it was?
Well, I think gravity is not.
Yeah, gravity. Yeah, I know gravity.
Well, gravity is not a fundamental force. It's an emergent force, and it's
That's-
got to come about after
Oh,
everything else settles out and mass accumulates.
I remember what it was that I wanted to say as a result of your talk about gravity, and that is I didn't really spend a lot of time talking about the Higgs field, but you'll all remember, I think back in 2017, there was a lot of press about discovering what was considered to be the God particle,
Yeah, the boson.
which was actually envisioned by Peter Higgs a long time before. Fortunately, he was still living when it was discovered. And the Higgs particle arises from, as you can imagine, the Higgs quantum field. It is the particle in the field that give all other particles mass. If in fact a particle has the ability to retain mass, like quarks and electrons and neutrons, it takes on its mass from the resistance offered by the Higgs field. So that seems like another mind-boggling concept that mass is actually imparted by a field and not inherent in a particle itself.
It is a mystery, isn't it?
It sure is.
What was that lecture series you mentioned at the Royal Institute? Who was
Well,
the guy?
David Tong,
David
T-O-N-G.
Thomas.
Yeah, TONG, that's all you have to do is look up David Tong and Fields. It's very engaging. I think it's an hour or so, but yeah, he's
There
a
are hundreds
real,
of lectures, and they're all fascinating. They're
Yeah,
experiments.
I go there all the time. Yeah.
yeah.
It's a wonderful lecture.
All right, let's see if we have a question here in the room. Is there any question here?
Yeah,
Anytime, sure.
so the imbalance between particles and antiparticles, why do we have, why
Yeah,
is there not antimatter?
yeah, yeah.
around?
Okay, the answer to that apparently is that at the moment of the Big Bang, you remember that the quantum level is not continuous, it's roiling. And it happened that at the moment of creation, slightly more matter was created than antimatter. And by the way, the difference between the two has been calculated, I believe, to be 1 in a billion. And that's partially derived from observations of the cosmic microwave background. Um, it appears that only 1 out of every billion particles of matter was left over after the matter and antimatter was balanced out and annihilated. That again is mind-boggling.
All right, any more questions in the room? Any more questions online?
Yes. Hi. Hey Phil, can you hear me?
Yes?
Yeah. So thank you for very insightful session.
You're welcome.
yeah, based on like your research, like, uh, what are the possibility that the universe is not real and we are living in simulation? And
Yeah.
yeah, yeah, and like, uh, also, like, is there any glitches or anomalies that we found in current universe, or the currently the way the particles and fields and their interactions that are there? That is there any anomalies that back that assumption that like we are living in simulation?
Uh, well, let me take the first question, then I'd like you to come back to me on the second. The idea that we're living in a simulation, of course, is one of these uh, many possibilities that we're basically a scientific experiment in somebody else's laboratory, and that perhaps we are, uh, you know, the dissertation, if you will, for someone's doctorate. The other possibility is the holographic universe. Now, in the holographic universe, I should point out, first of all, we all know what a hologram is. It's taking two-dimensional information and projecting it with a laser to create a very plausible three-dimensional image that moves and moves naturally. Well, because of something to do with the surface of black holes retaining information, there is a belief that maybe the entire universe, the information for everything, is actually painted onto its perimeter and then projected three-dimensionally throughout the intervening space. I mean, that unto itself just is incredibly mind-boggling because of the distance from one side of the universe to the other. But that's the essence of what could be a an illusion, if you will. And
Yeah.
then the second part of your question was, sorry?
Oh, is there any anomalies in the universe, the particles, the fields that they
Yeah.
interact with each other to back that um, back that assumption that like we are living in simulation, or like,
Yeah.
or either other side too?
Yeah.
Yeah.
Yeah. No, that's the other, that's a very good question. And it's one that has been taking, it's been thoughtfully researched, and there is complete uniformity. And as a matter of fact, one of the questions that was posed a long time ago was perhaps there's a corner of the universe that is composed or comprised of antimatter. And, somehow existing in harmony with everything else. Maybe that's where the antimatter went. But that's disproved because the border between our matter and the antimatter would be extremely energetic. It would be very, very visible, the interaction. And remarkably, the universe seems to be completely consistent in all directions. And the fields seem to hold up no matter how far they stretch. So
I
the idea of an illusionary universe, I think, just boils down to the idea of the science experiment in another universe, or perhaps the holographic theory.
Okay,
I,
got it.
can I ask one more thing? Do we have time? Are you saying,
Last one, Alan.
all right, if there's anybody who hasn't asked a question yet, now's your chance before I do that. Anybody?
Go ahead, Alan.
Okay. So if I'm hearing you correctly, wait, let me rephrase this. Am I being closed-minded or narrow-minded by believing that based on everything we know and can observe and can speculate from empirical data, the random universe is the most logical? Like, we're here asking these questions because it works.
Okay, yeah,
As soon
yeah,
as we ask questions like, how did the universe know
yeah,
to create 18 fields?
yeah.
We're
I
off
think
track, right?
I think the random universe is a possibility, but I don't think it is the most likely. And a number of scientists who have pondered this question have basically concluded the enormity of the number of universes that would have to be created. It would be like, you roll 200 dice and they all come up six. So
Sure.
what are the odds that you could finally roll 200 dice and get, 206s? That they're really infinitesimal. So the idea of a random universe is not well liked. There is more and more uh, credence as we delve deeper into our understanding of the universe, that something is behind it. And it could well be that it's Darwinian, that it just over a long period of time, it refined itself from complete chaos.
But that's still the same thing, though, isn't it? I don't mean to interrupt. I don't want to.
Yeah.
That's still the same thing, though. That's still 200 times rolling a 6.
No, there's one difference. And that is, here, I'll explain it very simply. You roll 200 dice, and if they're not all 200 in a random universe, you must pick up all 200 and roll again. But in a Darwinian universe, you roll 200 and then you cull out the 6s. And now you only roll the ones that are not 6s.
I see.
And over time, you get all 6s. So that's why the Darwinian theory actually has a lot more proponents.
Extended evolution.
Extended evolution, right.
Kind of cheap.
Survival of the fittest on a universal level.
It sounds like a teleological Darwinism, and I object.
Can I ask, is there time for one more question, or are we done?
3 hours. Let's call it a night. Thank you so much.
I'll be back.
Okay, too bad.
Catch you again. Thank you very
Yeah.
much.
Okay. Thanks, everyone. Appreciate your attendance
Thank
tonight.
you. This was fascinating.
Night, all.
I want to hear
Good
feedback.
night.
Bye.
Thanks, Michael.
Bye, everybody.
Thank you.